So 2 musical instruments, one playing at 400 Hertz, one playing at 406 Hertz. And with the different frequencies, if you're just standing somewhere else listening, you're hearing both of these sounds. And since you're hearing 2 sounds, that's going to lead to some interference. And it's a useful idea to set up a phase chart for this, looking at the total phase. And actually, we don't necessarily need the entire chart. We could just take a look at the formula for total phase difference. The difference in total phase, looking at just the stuff inside the sine function, we've got a 2 pi times, let me leave off the delta for now. We can attach the delta later. 2 pi times frequency times time. And we could write that as 2 pi divided by period times time. But I think times frequency instead of divided by period is going to be more useful because the sounds are usually listed as frequencies. Minus 2 pi x over lambda. And we're using minus because the sound is spreading out from the source. That's treated as going in the positive direction because it's increasing distance from the source as time passes. So that'll be minus. And possibly plus a phase shift. So that's the total phase. But we don't really care what the total phase is. We just care about the difference, comparing the 2 waves. So if you apply a delta to both sides of the equation, we're just looking at the change of each of these things. So change in total phase. And in this term, 2 pi times frequency times time, is there anything we can factor out? Anything that's not changing or not different comparing the 2 waves?
I would say like the 2 pi, the time.
Exactly. 2 pi can definitely be factored out. And both waves arrive at your ears at the same time. So we can factor out time. And usually we could also say there's no change, no difference in frequency. So if they were the same frequency, this whole term would be 0 because there's no difference. But since there is a difference in frequency, we have 2 different frequencies, there's also a delta frequency. And then for this one, what can we factor out? For the position term, the 2 pi x over lambda, what's not different between the 2 waves? Yeah, the 2 pi. Usually we would factor out the lambda as well. Usually we would get 2 pi over lambda times delta x because the waves are traveling different distances. In this context though, the wavelengths are not the same. These 2 waves have different frequencies and therefore they have different wavelengths as well. So the x and lambda are both going to be different. The waves travel different distances and the waves have different wavelengths. Of course, we can factor out the 2 pi. We just have 2 pi times difference in path length over wavelength, x over lambda. And then, of course, the 2 waves might have different phase shifts as well. So that would be the difference in total phase. When you're listening to these 2 waves, you hear a difference of 2 pi t times delta frequency minus 2 pi times difference in this ratio of how far the wave travels divided by its wavelength, plus delta phase shift. However, the really unique thing about this situation, the situation that shows up in this beats concept, when you've got sources producing different frequencies that doesn't show up in any other type of interference, this has a time term in it. This interference type changes as time passes. This term is time dependent. And this is unique amongst all of the stuff that involves interference. Every other type of interference we look at in this class, this term is gone. Both of the waves arrive at the same time. They both have the same frequency. So this time term is just 0, no difference. The other difference is how far it travels, the phase shift. Those don't change as time passes. So you just get one type of interference and it stays that way unless you move to a new location or change the sources somehow. But this one, we have a term that has time in it. That means the type of interference changes as time passes. as time increases, as the time goes by, you're actually going to be changing from constructive to destructive to constructive to destructive, which is going to lead to, what would that actually sound like? What does constructive interference sound like? What does destructive interference sound like?
With constructive, do you raise the pitch?
Not the pitch in this case. The pitch is more about the frequency. So the frequency determines what note, what pitch you hear.
The loudness?
Right. The amplitude, which is what's really influenced by interference, is all about the loudness, the volume of the sound. So constructive interference would make it sound louder. Destructive would make it sound quieter. So if you've got an alternating interference, as time passes, delta phi changes from an odd multiple of pi to an even multiple of pi, so like 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. That means we're alternating between loud and quiet and loud and quiet and loud and quiet, possibly many times per second. So what you're actually going to hear is this weird, annoying sort of wobble between loud and quiet and loud and quiet and loud and quiet. And this sounds really annoying. It's a terrible sound. This is why instruments sound bad when they're playing together and they're out of tune. Because what you hear is beats. Beats is just this phenomena of this alternating loud, quiet, caused by the fact that there's a difference in frequency, which means the difference in total phase changes as time passes. And of course, there's all this other stuff as well. But what variable does not show up in any of these terms? Yeah, these do not have time in it. These are time independent. In other words, this entire thing is just some constant. And the value of that constant depends on the sources and how they're related to each other, depends on where you're standing, depends on the wavelength. But assuming none of those are changing, this is all just some big constant. So we end up with delta total phase equals 2 pi times delta frequency times time plus a constant. So that means ignoring this constant, because we don't really care what that constant is. We don't really care about the value of delta phi. We just care about, is it a whole number of cycles or something and a half cycles? That's going to update, like let's say you're looking at a constructive interference. Constructive interference suggests that delta phi is what sort of value?
It's the odd multiple of pi.
That's going to get you destructive.
Oh, sorry, it's the even.
Right. An even multiple of pi is a whole number of cycles, so that gets you constructive interference. Let's say you wanted to get to the next constructive interference. Like let's say you're going from 8 pi to 10 pi. That's a constructive, a time when the interference is constructive, and then the next time when an interference is constructive. So from one instant when it's loud to the next instant when it's loud. That amount of time corresponds to a difference in delta phi of plus 2 more pi. So every 2 pi, the cycle repeats itself. Every 2 pi worth of delta total phase. If you're listening and it's currently loud, then 2 pi radians later, it's going to be loud again. But to convert that to an amount of time, if we want to know the amount of time from loud to loud, we can say delta phi changes from 8 pi to 10 pi, or from 10 pi to 12 pi, or 12 pi to 14 pi. In other words, this is changing by 2 pi. We can ignore the constant because that's not changing as time passes. We just want to know how much time does it take for this to increase by 2 pi. And the amount of time it takes is usually called the beat period. So the beat period just means the amount of time it takes from loud to loud or from quiet to quiet. And how would you solve that for beat period here? How would you solve for the amount of time it takes to go from loud to the next loud? if we want an increase of delta phi of 2 pi, we want to go from even multiple of pi to the next even multiple of pi, so that's increasing by 2 pi. That has to equal 2 pi times the amount of time from loud to loud times the difference in frequency. And we can ignore all this because it's a constant, it's not changing. So how would we solve for the beat period then, the amount of time it takes?
You just divide by 2 pi and the change in frequency?
Yeah, if we divide both sides by 2 pi delta f, then we're going to have beat period equals 2 pi's cancel out, so we just get 1 over the difference in frequency. Or alternatively, we could invert that, raise both sides to the -1 power. The inverse of beat period would be called beat frequency. F beat. And that's just going to be difference in frequencies. In other words, F2 minus F1. Or F1 minus F2. I would just say you can subtract it in either order, but take the absolute value because we want it to be a positive result. So that's how you would calculate what's called the beat frequency. The beat period means how many loud, quiet, loud cycles happen per second. Sorry, other way around. The beat period is how much time it takes from loud to quiet to loud again. The beat frequency is how many loud, quiet, loud cycles happen per second. And you can calculate that beat frequency just by taking the difference between the two frequencies of the original sounds, the sounds created by those sources. And in this case, if you take that difference, we've got one trumpet creating a 400 hertz sound and another trumpet creating a 406 hertz sound. What's the difference between those?
6 hertz.
Right, so that means when you're listening over here, you're going to hear a beat frequency of 6 hertz, 6 cycles per second. And 6 hertz is not the pitch of the sound at all. So, 6 hertz sound, if that was actually the pitch, would be too quiet, or not too quiet, too low to even hear. That's beyond the usual range of human hearing, if I remember correctly. But 6 hertz is not the pitch of the sound. 6 hertz is how many loud, quiet, loud cycles you hear every second. So the sound from these trumpets is going to sound like one sound that's wobbling loud, quiet, loud, quiet, loud, quiet, loud, quiet 6 times per every second. Meanwhile, the pitch you actually hear, what we call the carrier frequency, is just the average of these. If these are close enough, they're going to seem to blur together in your mind to just one sound, whose pitch is halfway between those. So what's the average of 400 and 406? What's halfway between those?
403.
Right, so that would be the carrier frequency. So the carrier frequency in general is just the average of F1 and F2. And that tells you the actual note you hear. It's just the average of those two notes. So what you're going to hear, and note that this is true no matter how far or how close you're standing, because the X term is a constant and doesn't influence what happens as time passes. What you hear is, instead of hearing the 400 hertz note and the 406 hertz note individually, they seem to merge together in your mind into one 403 hertz note, but it's going to sound like it's wobbling between loud and quiet 6 times every second. And that's what we call beats. One beat is one loud to quiet to loud alternation. Any questions on the algebra of that so far? And let's take a quick look at what that would look like as a graph. If you have a wave and you want to add in another wave to get interference, let's say they both start off at a peak together. But then the other wave has a slightly shorter wavelength. So we have waves that look something like this. They start off in sync with each other. At the beginning, they're both at a crest. So that would be constructive interference. But then a little bit later, they're not quite matching up. So we're going to get partial interference. Then a little bit later, we now have a crest and a trough matching up. So we get destructive interference, or close to matching up anyway. And then a little bit later, crest and crest partially align. So we get partial interference. And then a little bit later, we're back to crest and crest again. So this is going to alternate from loud to quiet and back to loud again. So if you combine these waves, we can see we're going to get alternating interference. And what this would actually look like if you were to combine these waves together, you're going to get, let me dull this out a little bit. In situations where they're matching up, crest and crest, we're going to get a very large wave. And then the wave is going to get smaller and be almost flat here, and then get larger again. So we're going to get something like that. We're going to get a wave that's very large amplitude and then becomes smaller amplitude and almost flattens out completely, and then gets to be larger amplitude. And so we're going to alternate cycles. And let me draw a more detailed version of that so we can see where beat period versus carrier period come in. If you have a wave that looks like something like that. So it's alternating between loud and quiet and loud and quiet and loud. The carrier period would be the time, assuming this is a time versus Y graph. The carrier period would be the amount of time from crest to crest. So that's the carrier period, crest to crest as usual, or trough to trough would also be the carrier period. And that should be the same throughout. Like this amount of time should be the same carrier period from crest to crest. Whereas the beat period would be the amount of time from loud to loud. So for instance, this is a loud time. This is the next loud time. This amount of time would be the beat period. Amount of time from loud to loud, or from quiet to the next quiet. That would also be the beat period. So carrier period is actual crest to crest of the sound wave, even though the crests are changing height. Beat period is the amount of time from loud to loud or from quiet to quiet. And then of course the inverses of those would be the carrier frequency and the beat frequency. Any questions on that so far?
So carrier frequency or the beat frequency is going from loud to quiet?
Loud to loud, one complete cycle.
Okay.
So the beat period is the amount of time from loud to quiet to loud. And that's typically going to be many times per second. Like this 400 hertz and 406 hertz example we were looking at, that's a difference of 6. So that's going to be 6 loud, quiet, loud cycles every second. So one full second would be wow, 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 wow. That's 6 cycles in 1 second. And as this happens faster and faster, it's just going to sound more and more annoying. In fact, the more out of tune they are, let's say you had like 400 hertz and 410 hertz, that's going to be 10 loud, quiet, loud, quiet, loud, quiet cycles every second. So the beats get closer and closer together in time. They come in faster and faster, and it just sounds more and more annoying. At some point, though, these are different enough that your brain starts to distinguish them as different notes, and that's not so bad. In fact, maybe even you have different notes that form a chord, a nice, neat interval between the notes. On the other hand, let's say you make these more in tune. As these get more in tune with each other, let's say this 400 hertz stays as it is, but the 406 hertz goes to, let's say, 404 hertz. Now what's the difference between these?
4 hertz.
So you're only going to hear 4 cycles per second. And then as this gets even closer, let's say 402 hertz, now you only hear 2 loud, quiet cycles per second. And of course, the average is going to be 401 hertz. And let's say you get to the point where it's 400.1 hertz. At this point, what would be the beat frequency? What's the difference between those?
Just 0.1.
Right, 0.1. In other words, 1/10 of a cycle per second. So if the difference between these is only 0.1 hertz, that means you only hear 1/10 of a cycle per second. In other words, 1 cycle every 10 seconds. And if it takes 10 seconds to go from loud to quiet to loud, that's so long you're not really going to even notice it. At this point, these are going to sound like they're practically the same note. And this is a very useful way to tune instruments. If you have 2 instruments or 2 strings on the same instrument that are supposed to be the same pitch, the same note, if they're exactly in tune, you won't hear any beats. It'll just sound like a steady amount of loudness the whole time. If they're out of tune, it's going to sound like it's wobbling between loud and quiet and loud and quiet. So this is a very practical way to tune instruments by ear, even if you don't have an electric tuner or anything like that. Any other questions on that?
Yeah, sorry, once more. The difference between beat frequency and beat period. Like I'm still a little bit confused.
The beat period is the amount of time it takes to go from loud to the next loud. Whereas beat frequency is the number of those cycles every second.
Oh, okay. Thank you.
So for instance, a beat period of 3 seconds means it takes 3 seconds to go from loud to quiet to loud. That would also mean a beat frequency of 1/3 hertz, which means you only get 1/3 of the way from loud to the next loud over the course of a second. So it's exactly the same as the usual relationship between period and frequency. They're inverses of each other, cycles per second versus seconds per cycle. But for beats, we're not talking about the individual oscillations of pressure. That's the sound wave, that's the carrier wave. We're talking about the cycle from loud to quiet to loud. If it helps, you could even sort of outline that. This curve is often called the wave envelope. It's almost like a larger wave that the oscillations fit inside. So this green curve here would be called the wave envelope, and 1 beat period is the amount of time from large to large on the wave envelope curve itself. And that's often a very convenient way of thinking about waves that change amplitude as time passes. If you've got a wave that changes amplitude, you can just mark all the high points and low points and draw curves connecting them. And that basically forms boundaries that the wave fits inside. And those curves are called the wave envelope. Any other questions on that? All right, send me an email if you want to request any topics for next time, or if you have any other questions, and I will see you next week.
Thank you.
You're welcome.